As we did on Wednesday, let's start the day today by talking more about power series in this case, but we want to apply it to differential equations. So the first part of class today is going to be an introduction to power series solutions of differential equations, diffie-qs for short. And we'll restrict our attention to a couple easy examples, okay? And for the homework due Monday, there will be one relatively easy example. If you take differential equations with Dr. Alk next spring, I think he does a fair amount of this. If you take diffie-q with linear with me in the fall, I don't do as much of this, but I do a little bit in a certain special case. So let's consider an initial value problem, IVP. And let's make it be fairly simple. So let's say dy dx equals y. I'm purposely here making my independent variable be x now, even though we usually use t, just for emphasis that you can. There's certainly some applications where time is actually not the independent variable, and you might prefer using x. But the assumption here is that x is independent and y is dependent. And let's say y of 0 equals 1. Now, this is actually a pretty easy equation to solve. In fact, you could even guess the solution, and I think you should be able to, but let's take a more complicated approach and see that we get the same answer. And that will have the benefit of generalizing to differential equations that are harder. Let's assume that the solution not only exists, but can be represented as a power series. Can be represented as a power series. Centered where? Well, since the initial condition is that when the input x here equals 0, it probably should be centered at x equals 0. If I had a different initial condition, maybe y of 3 equals 1, it's better to center it at x equals 3 in that case. But it's 0, so let's center our power series at 0. There's the constant term, then the x term, then the x squared term, then the x cubed term, then the x to the 4th term, etc. That would be my assumed form of the solution as an infinite series. It is an assumption. That assumption could be wrong in general. But certainly with simple examples like this one, it does end up working. Is that a Taylor series? Every Taylor series is a power series, right? It's an infinite sum of powers of x if it's centered at 0, and x minus something if it's centered somewhere else. Is every power series also a Taylor series? It depends on whether your interval of convergence is just a point or an entire interval. If it is an entire interval, then yes, your power series is a Taylor series for whatever function it defines, actually. In general, it might not be a well-known function. The goal is to figure out what the a's are. So you got to look at the differential equation. Its left-hand side is dy dx, and its right-hand side is just y. In fact, I've already got the right-hand side here. If it was more complicated, like y squared, we will do that example next. With a y squared there, then I'd actually have to square this to get how the right-hand side simplifies in terms of x. Assume you're in the interval of convergence where theoretically you can prove that you can differentiate term by term. The derivative of a constant is 0. The derivative of a1 times x is a1. The derivative of a2 times x squared is 2a2x. The derivative of a3x cubed is 3a3x squared. The derivative of a4x to the 4th is 4a4x cubed, etc. These two things are supposed to be equal to each other for all x in possibly some small interval centered at 0. The only way that's going to happen is if the like terms coefficients match. So the constant terms have to match. The coefficients of x have to match. The coefficients of x squared have to match. The coefficients of x cubed have to match, etc. This gives us really an infinite sum system of infinitely many equations to solve. It's not as bad as it sounds. Turns out to be a pretty nice pattern that happens. First note, the initial condition is that y of 0 equals 1. 1 equals y of 0. If I plug that into the original assumed formula here, replace x with 0, I get a0 plus a1 times 0 plus a2 times 0 squared, etc. That all simplifies to a0. A0 is the initial value. If it were, say, a 3 instead of a 1, then a0 would be 3. Now use the other equations. The equality between a1 and a0 means a1 equals a0, but a0 is 1, so a1 is 1. Look at this one. 2a2 must be a1, so a2 must be 1/2 a1, which is the same as 1/2 a0, which is 1/2 times 1 is 1/2. Go to the next one, 3a3 equals a2. 3a3 equals a2. So a3 is 1/3 times a2. Ultimately, 1/3 times 1/2 times a0, 1/6 a0. A0 is 1, so this becomes 1/6. Next one, 4a4 equals a3. So a4 is 1/4 times a3. In terms of a0, that ends up being 1/24 a0. A0 is 1, so this becomes 1/24. I think I'm seeing a pattern, do you? 2 is 2 factorial, 6 is 3 factorial, 24 is 4 factorial. I'm not proving it, but that pattern does continue. An is 1 over n factorial. And therefore, y equals, going back up here and replacing all the numbers in place of a0 is 1, a1 is 1, so I get 1 times x. a2 is 1/2, that gets multiplied by x squared. a3 is 1/6, that gets multiplied by x cubed. a4 is 1/24, that gets multiplied by x to the 4th, etc. Yeah, we've seen this quite a number of times, haven't we? What's this function equal? Somebody over there. What's this equal? Something very familiar. E to the x. We could have figured that out without doing all this, right? We're after a function whose derivative is always itself and goes to the point 0, 1. E to the x has a derivative always equal to itself, and e to the 0 is 1. It had to be e to the x. Okay, so this problem is much easier done just by even guessing. You don't have to do all this. Well, let's do a more complicated example where it is helpful. Question?
How do you know that A0 and A1 are equal?
Yeah, coming back up here, I figured out how the left-hand side and right-hand side simplified in terms based on this assumption. And you want these two power series to be equal for all x in some interval around 0. The only way that's going to happen is if the constant terms are equal, if the coefficients of x are equal, the coefficients of x squared are equal, the coefficients of x cubed. All the coefficients have to match. And that's what gives me these equations that I can solve. Here's a more complicated example. dy dx equals, let's make it y squared. Let's still make the initial condition y of 0 equals 1. That will make things a little simpler. Once again, assume y is represented as a power series in powers of x with unknown coefficients. Same thing as before. And in fact, in this case, the left-hand side is the same thing as before. dy dx is still the same thing. It's the derivative. 0 plus a1 plus 2a2x to the first power plus 3a3x squared plus 4a4x cubed, etc. But the right-hand side is y squared. It's more complicated. I have to square this power series. We've done that kind of thing before, actually. Remember that day, week and a half or 2 weeks ago, where we multiplied series, we also divided series and differentiated and integrated them. We also talked about the most beautiful equation in the universe that day. It was my favorite day of class, actually. Let's multiply these two series, in effect, squaring y. This is y squared. Same general principle is going to hold. If after squaring this out, I want it to always equal this thing when x is close to 0, that's only going to happen if the coefficients of the like terms, the like powers of x, are the same. Multiply. Start with the first term on the left, multiply times every term on the right. A0 times A0 is A0 squared. Then I have A0 times A1x. That's exactly what I just said. Then A0 times A2x squared. Then A0 times A3x cubed, etc. Now go to the second term on the left, multiply it times every term on the right. Put the answer below the first line, line up like terms vertically, same powers of x. A1x times A0 is A0 times A1x, same term as on the first line. For the next one, I have A1x times A1x. That's A1 squared times x squared. Something different than this one. And then I have A1x times A2x squared. That'll be A1 times A2x cubed. Don't stop. Let's go a couple more lines with a couple more terms here on the left. Go to the A2 times x squared, multiply it times everything, times A0 gives A0 A2x squared, times A1x gives A1 A2 x cubed, etc. This will be our last one that we do. A3x cubed times these things times the first term is A0 A3x cubed, etc. And this is supposed to go on forever and ever. Is this valid? Can I do it? The answer is yes. That takes proof. We're not proving it. It's beyond the scope of this course. We are blissfully ignorant of what it takes to prove that you can do such a thing. Combine the like terms now. We only have one constant terms. We have two x terms, and they both have the same coefficient, A0 times A1, so that we get 2A0 A1x. With the x squared coefficients, two of them are the same. You get 2A0 A2 plus A1 squared times x squared. And combining these three things here to get this. The next one's going to be the x cubed term. You've got two of each kind there. You've got a 2a0, a3 plus 2a1, a2 times x cubed, etc. We won't worry about the higher order terms. Should you worry about the higher order terms? Yes, you really should. But we're only trying to do an introduction here, so this is good enough for us. Yeah, there we go. This is supposed to equal that for all x near 0. So now equate the coefficients. And also use the initial condition. 1 equals y of 0, just like before. Replace the x's with 0 and it simplifies to a0. A0 is the same as the initial value of y, which should make sense. dy dx, remember, was a1 plus 2a2x plus 3a3x squared plus 4a4x cubed, etc. The constant terms are these two. These have to match. The x terms are these two. They have to match. The x squared terms have coefficients that are this and this. Those have to match. And the x cubed terms are this and this. Those are the coefficients. They have to match. So the equality between these two implies that a1 equals a0 squared, but a0 is 1, so this is 1 squared, which is 1. Using the fact that a0 is 1. If a were 0 or not 1, like if this were a 3 there, that would imply a0 is 3. a1 would be 3 squared, 9. So this is only turning out to be equal to a0 because I picked a0 to be 1. The next equation, 2a2 equals 2a0 times a1. In other words, a2 is a0 times a1. Both of those are 1s. In other words, a2 is also 1. For the next equation, 3a3 has to be this. So a3 must be 1/3 times 2a0 a2 plus a1 squared. But all the numbers inside the parentheses there, a0, a2, and a1, they're all 1s. This simplifies to 3. 1/3 times 3 is 1. I think I see a pattern. All these a's seem to be 1. Let's try one more. 4a4 equals this. So a4 is 1/4 times 2a0 a3 plus 2a1 a2. Of course, I could factor out that 2 and cancel with the 4. But I can also leave it as it is. This is a 4. 1/4 times 4 is 1. The pattern seems to be that every a is 1. That's not a proof, but it does turn out to be true. And this means your proposed solution is y equals, all the a's are 1. So it's 1 plus 1 times x plus 1 times x squared plus 1 times x cubed, etc. Hey, that looks familiar too. That's a geometric series. It equals 1 over 1 minus x if the absolute value of x is less than 1. So even though this example was harder, it does still turn out that the answer is something easily recognizable. Let's confirm this with separation of variables. dy dx equals y squared. Separate variables, get the y's on the left and the x's on the right. Divide both sides by y squared, which means multiply both sides by y to the -2. And yes, go ahead and pretend dy dx is a fraction and pretend like you're multiplying both sides by dx. You see something like this, you integrate both sides. As usual, this side integrates to something simple, x plus c1. This one's not too bad. You don't get a natural logarithm, you get a negative y to the -1. You might write plus c2, but you would subtract that c2 from both sides anyway, so we don't have to. Multiply both sides of the equality between this and this by -1 to get rid of the negative sign there. We're trying to solve for y. So y to the -1 would be -x plus c, where c is -c1. Now just take the reciprocal. Y will be 1 over this entire thing. This is looking good, isn't it? Use the initial condition. Y is 1 when x is 0. To substitute, 1 equals 1 over -0 plus c, which is 1 over c, and therefore c is 1. Therefore, replacing c with 1, I can write the solution like this. Same answer we got with the power series. The power, this function, in a sense, does solve the differential equation for all x except 1. On the other hand, the power series technically only converges when the absolute value of x is less than 1. So technically, this only works when x is between -1 and +1. It's not a big deal. When you're doing this kind of thing, you're most interested in the solution near the initial condition.